And we're back again. Time for our next session, and we are going to go to Fulvio. And Fulvio, before I even start, I want to apologize for having a misspelling in your last name on our agenda slide. The U key and the I key are a little too close together for me sometimes. Similar to our first session today, one of the great things about ScaleX is learning about brand new technologies that I hadn't known before ScaleX was coming together. Fulvio is going to be sharing with us some details on a project called Liqo, which will manage clusters of clusters in Kubernetes. So think big clusters. And Fulvio, with that, I'm going to let you go into the details because you're going to be a lot better at it than I am.
Thank you. Thank you very much, Gary. Okay, so let's start with this project that we started a couple of years ago. Actually, we started the discussion exactly 2 years ago in the KubeCon Europe when it was in Barcelona. And this project is about creating a sort of endless Kubernetes ocean. But let's start from the beginning. And the beginning is not exactly Kubernetes. The beginning is that we have services. We have a lot of microservices. And we would like to have those microservices to fly around and let them find the best place available for them to be executed. So in principle, it doesn't seem so new because, this is exactly what we do in data centers. So we start a pod and the scheduler Kubernetes decides which server has to be used and then the pod runs. But what about if we have a different environment, like we have a different number of clusters? So in the previous talk, BBVA talked about having, if I understood correctly, 24 clusters. So we are in touch with companies that have more than 100 clusters at the same time. And when you deploy a pod, the pod is free to fly inside the cluster, but it cannot fly outside the cluster. So a cluster is a sort of container that you cannot go outside. And this is a big problem in terms of management, in terms of resources, because maybe you want to have a sort of unique cluster, a sort of super cluster that unify all your clusters. So for different reasons, for security, for geographical distribution, for scalability, so this is where Liqo comes. So overcoming this limitation of being able to float, to fly inside the cluster. Going a little bit further in terms of future, this can be even worse if we think about the Internet of Things domain. So here we have billions of devices and fog nodes and data centers on-prem or on public cloud. And we would like to float, to allow our services to float so that when we run a service, the service will experience the best location either nearby, maybe in a device or fog node nearby, or in the cloud or whatever. So basically, we are not longer interested in having our services running on our devices. Let them find the best place for them to go. I think
I'm sorry, Fulvio?
Yeah.
Sorry, could I just interrupt? Are you sharing slides at the moment?
Yes.
We're not seeing anything at the moment.
Yes, I'm sharing the slides, but I completely forgot to launch the command. Haha, my fault.
Ah, brilliant. Thank you very much.
I was
Thank
sharing.
you. We didn't want to miss out on the excitement. Okay, thank you.
Sorry. So you missed the fantastic slide that was before. So, okay, let's go. It's better. Okay, so here we come to the meat of the Liqo project. Liqo stands for liquid computing, and this idea of having computing available everywhere, and we allow our apps to fly around in order to get the best place for them. Of course, this is the first ingredient. The second ingredient is controlling the application. So we would like to set some policies that allow my task and my data where they can go, because maybe it's fine to have an infinite ocean of resources, but maybe I would like to avoid some pieces of those resources, maybe a provider I don't trust, and so on. And the third ingredient is ownership, because, you know, maybe resources are not all mine. So maybe I share resources or I borrow resources from another company, another provider. So I would like to be in control of what I share and what I get. So basically, that's the third pillar. In this talk, I will focus on scalability. So I will focus on the first item, so flying. So I don't talk about controlling and ownership, because this is another very important aspect of Liqo, but I don't have time today. So let's think about how we can use this liquid computing. So we have different clusters. The cluster is the basic ingredient in our vision. What is a cluster? A cluster is a part of the data center, but we were talking about Internet of Things. So obviously also a car can be a cluster, a rack of machines can be a cluster, an embedded device can be a cluster. So what should I do? First, I should discover which are the clusters that are available. And once I discover the clusters, they have to advertise to me what they are willing to share. And then, of course, I have to accept the offer if I agree, and then peer. The peer term is very important for us. And I mean, this is a talk organized by Cisco, so I assume that people are very familiar with networking. We feel that this model looks very much what we are used for with BGP in the traditional old days of networking, in which we peer different networks, different autonomous systems. We use the same concept here. So we peer with a specific cluster and we start exchanging data and resources. And of course, we can use them. And at some point, we can de-peer. So this process is very dynamic, and we can start and stop peering in a very flexible way. How does it work? So the basic idea is that we have a cluster we call home cluster. The cluster is composed by different nodes. Those are physical servers. But in addition to the physical servers, in our architecture, we create what we call big nodes. Big nodes are virtual nodes, are not physical servers, but they are abstracting a remote data center, a remote cluster. So I can have a huge amount of remote cluster. We call them foreign clusters, each one hosting some nodes, physical nodes, some services, some pods, and so on, which are all duplicated here. Let's say we can create a sort of shadow copy of the resources of our pods in our big node. So in our main cluster, our home cluster, we have a set of physical nodes and a set of virtual nodes. Each virtual node summarizes what we have in a remote cluster we're pairing with. Obviously, there are a couple of very important ingredients here. First, that this kind of virtualization is done by the virtual kubelet. We greatly extended the virtual kubelet in order to do this kind of realignment between home cluster, so the big node in the home cluster, and the foreign cluster that is actually abstracted by this big node. Second, we have to implement a sort of reflection service. that allows to duplicate in a clever way. We will return here in a clever way later, all the things that we started in the remote cluster so that they are apparently available also locally. So when I interact with my home cluster, I can see all the pods, all the services, even if they are running remotely. And this is the reflection part. And definitely, we need a seamless network connectivity across the big cluster, because even if I'm trying to reach a service or a pod in a virtual node, actually, this has to be redirected to the remote cluster. So the network has to provide this kind of seamless network connectivity across all the cluster. Again, also this will be briefly investigated later. And finally, please note that this model is completely compatible with the standard Kubernetes or K3S. So yes, we support also Rancher control plane. So we don't need to use anything special to interact with our cluster, just kube control and everything that we are already using. So no changes needed in the user interface. So, okay. We presented briefly how the Liqo project works. So now let's introduce the scalability challenges that we are going to face. Not everything is already implemented, but this is, let's say, our journey toward scalability. And we can split our problems in terms of scalability in 3 big sections. The first is scheduling. The second is how to connect to a remote cluster and reflect the services that we have there remotely. And third, how to decrease the volume and the frequency of state information that you have to share one cluster to the other, because in the end, if you don't decrease the amount of information, the scalability will be greatly affected. So let's start with the first, multi-level scheduling. And I think this is pretty simple considering how the model works. So you have a pod, and the pod is then consumed by the first scheduler. The first scheduler decides the best location, so it's a standard vanilla scheduler in Kubernetes, and maybe it decides that the best place for that pod is a big node. So this big node is actually a virtual node, so it's taken by Liqo. So Liqo does the magic and basically creates a virtual pod here in this node, and then decides where to schedule. So it moves the pod to the second level scheduler, so the scheduler that is in the foreign cluster that has been selected, and finally, the node that will be selected will accept the final pod. So, you know, it's pretty easy, this kind of multi-level scheduling, that we are splitting the schedule decision in multiple steps. So first, we decrease the pressure on a single schedule. So our cluster can be virtually bigger. And second, we can potentially increase the accuracy of our scheduler, because, you know, if your scheduler becomes more scalable, you can add more information, so more accurate scheduling in your cluster, like having more constraints or adding more parameters that can be used to select your best location for your services. Please consider that although we didn't do that so far, theoretically an n-level scheduler is possible as well, because, you know, we're just drawing here a couple of levels, so home and the first foreign, but nobody prevents a foreign cluster to have even there a virtual node and then increase a new level of schedulers here. Second section about scalability is how to handle connections. So let's start with the first. Here you have a home cluster, and this home cluster is setting up a set of peerings, a lot of peerings with other clusters. And basically, all those are peerings. And what happens is that in the end, what the home cluster perceives is to have a sort of virtual cluster, very big, huge virtual cluster, which is this green virtual cluster here. So in the end, when it starts a pod, it's like the pod has all those resources together. So a very huge cluster, virtual cluster there. So the problem here is that we have to create a sort of uniform address space, because all this cluster here needs to allow each pod to reach all the other pods and services and so on. So we have to create a sort of uniform addressing space for pod and services, despite possible IP overlaps. We have netting and blah, blah. But the problem is, what about now if I want to start a service and a pod that starts here in the green cluster and another pod starts here in the orange cluster? This is completely possible because they are part of the same virtual cluster. But what about the communication between those two pods? So should we allow communication to go to the home and then go to the orange pod? Probably this is not the best way to go. So direct communication would be much better. So here it is, direct communication. But direct communication means that the address space should be really coherent between all those clusters. So in each cluster, we have to declare and handle a sort of address mapping table, so that the addresses that are actually in cluster 3 are translated into addresses C3 first, in order to allow this direct communication. And the reason is that when you peer with another cluster, you have no idea which addresses are used there. And there's a chance that your addresses and their addresses are exactly overlapped. So you have to disambiguate this kind of situation. So, okay, each cluster has to create a sort of address mapping in order to allow point-to-point, peer-to-peer connections. But things can be even worse, and now the picture becomes very, very much complicated, because if you take another cluster like C7, okay, but C7 can create its own virtual cluster. Please be careful. C7 is part of the virtual cluster created by cluster 0, but cluster 7 can create another virtual cluster on its own because it's completely independent. So in the end, here it is, another virtual cluster, the yellow cluster, that comes, okay, both in parallel running together. Okay, so what's the problem here? The problem is that our C8 cluster is currently being part of multiple virtual clusters. It's part of the green virtual cluster, but it's part of the yellow virtual cluster. So the address mapping that we have to do here becomes much more complicated, and potentially it can explode in complexity, because we have to create some mappings which are used for the virtual cluster C0 and some other mappings that are used for the virtual cluster C7. So definitely we need to implement a clever logic to create mappings only when needed, not just create a full mesh which can explode, because not only a full mesh, but an full mesh in parallel, but we have to create something look like a full mesh, but in a much very clever way, which is something that we plan to do, but we are not there yet. And what about data reduction? Data reduction is the third pillar that we have to follow in order to achieve scalability. And the first data reduction is about volume, so reducing the amount of data. There are different things that we can do. This is just an example. an example is, okay, we have 3 nodes here in a foreign cluster, and of course, the Kubernetes control plane knows there are 3 nodes. But if you look at the home cluster doesn't see 3 nodes, just see a first node. So just one node, which is the virtual one, because in the home cluster, all the physical remote nodes are modeled with a single virtual node. So this is an example of a reduction of data volume in your home cluster. By the way, a very nice byproduct here is that if we increase and we add a new node in the foreign cluster, it doesn't change anything in the home cluster. The home cluster still has one node, okay, one worker, which reminds me the old days in which I was working about routing in the internet, and we say, okay, we don't want to create too many updates in foreign domains because this increases this stability of the routing. So less updates means more stable routing. Again, exactly the same principle. So not less data, but also less updates. And frequency. Okay, frequency means do we have to react to all the events that happen in Kubernetes, or we can maybe do something smarter? Definitely, we can do something smarter. So let's make an example. We create a pod here, and maybe the pod is undergoing into different states before it's ready to go. I mean, it's ready to be used, as to pass different stages. Do we have to transmit all those stages to the home cluster when the pod is creating a foreign cluster? Obviously not. So maybe the pod creates different states, different events, but we have here a very clever Liqo event filter that reacts per event, because not all events are created equal. So some can be filtered, some can be aggregated, some have to be passed as they are. So this clever logic will do the magic and will only send the proper events that are actually required in the home cluster. So we decrease the frequency of the updates in our way to better scalability. Another example here. Let's imagine that you have a node here, a pod running on a node, and unfortunately the node fails. So of course, the foreign cluster will be able to reschedule the node and then restart the pod, so reschedule the pod, sorry, and restart the pod on another node. Do we have to tell the home cluster that I did this? Probably not. So probably it's enough if I'm able to reschedule the pod successfully on another remote worker is enough, and I don't have to update at all the control plane, again, for better scalability. Final technique that we use to reduce or to increase the scalability is to have a better control of the control plane load. The control plane is very important in Kubernetes because it's the supervisor of your entire cluster. So again, this is something that we can achieve thanks to our hierarchy. So what can we do? Let's make an example. We create a pod here. So we create an endpoint actually. So basically we increase the number of replicas of a service. But you know, when you increase the number of replicas of a service, you have to tell to the control plane that you increase one more replicas, but definitely you have to update all the other nodes which are watching that information, because now you have one more endpoint. So all the load balancers that are across the Kubernetes cluster needs to know that there is one more servant that is available for you. So, you know, you tell the Kubernetes control plane about these new replicas, and then the Kubernetes control plane has to update all the objects who were watching for that event. But definitely, this has to be updated in the home cluster as well. So here it is. You update Liqo, you update the control plane, and here you update all the nodes that are available there that are watching for that event. So apparently there is no advantages here. But if you look at the pressure on the control plane, it's much better now because you have two control planes and each control plane has to update only the local nodes. So your home cluster has to update only the local nodes here, and it doesn't have to sustain the CPU and the traffic required to update all the remote nodes. Okay, so again, also here is something that goes in favor of better scalability. So I'm at the end of the talk. So this is our initial initial way to Liqo. So this idea of building our endless Kubernetes ocean. We're at the beginning, so there is a prototype that works. We are really working hard in order to make it even better. Not everything that I presented here is already implemented, but this is definitely in our roadmap. For more information, you can check the website and definitely the GitHub. It would be a pleasure if you like the project, if you start it, because that's a big push for us. And this is the end of my talk. I thank you for the attention and ready to answer to any question you may have.
Thank you very much, Fulvio. Let's see if we have any questions from the attendees. Let's see down here. Oh boy, there's a big one down there. Okay, so so here we go, Fulvio. Can you see the question in the Q&A at the bottom right?
I'm not seeing the.
Okay, so I will go ahead and read it. Can vanilla Kubernetes resources be used to manage them, or some CRDs must be used to do that? For example, if I want to allow or deny traffic between virtual clusters, should I use vanilla networking policies, or would I need to use ones defined by Liqo? And then there's a second part, but I'll let you go ahead and do that one first.
Okay, thank you. Yes, so our ambition is to reuse the most that we can from the standard tools and so on. So even with the network policies and so on, our ambition is to allow standard tools to be used. Consider that we don't impose any constraints on how the cluster looks like before making the peering. An example, when I peer one cluster with another, I cannot know which network provider is there. So maybe I have a Cilium on one side and I have a Calico on the other. I really have no idea. So if we use standard things, is much better in order to guarantee this kind of interoperability. So we are not there for the policies yet. So we're focusing on duplication of services and so on, pods, services, and so on. But definitely our ambition is to reuse what is already there.
Okay, great. And then the second part is also defining a big node goes through kube control, or how?
Define a big node is completely defined by Liqo when you peer. So there is basically we use a new CRD in order to peer. So it's like having a network protocol asking the other cluster, do you want to peer with me? Yes, you know. And then the other, you need to have a Liqo installed on both clusters, of course, in order to peer, but the local Liqo will create all the resources that are required for you to do the magic.
Let me just see if we answered the questions. Just seeing if we get a response here real quick. All right, well, I think we are set. Ellis, have we answered the question, Ellis? Yes, perfectly. Okay, we're good.
Okay, thank you.
Fulvio, thank you very much. Any other questions? If there, you can also follow up and ask questions in our Slack channel, and we'll get back to you if we missed you. Fulvio, thank you again very much for your time and all the expertise and knowledge. And